Hi everyone. In this last video of the series, we learned how to reduce inductors connected in series and parallel to one equivalent inductor. So as a reminder, inductor is a dynamical element whose voltage-current relationship is given as follows. V, the voltage drop across the inductor, is equal to L di dt, where L is the inductance, I is the current through that inductor. Integrating this equation, we can get the current through the inductor as the integral of the voltage across the inductor divided over 1 over L. So let's start with a series network. So here I have two inductors in series in the circuit, and the circuit is supplied by one voltage supply Vt here that is sourcing a current I. I'd like to reduce the circuit to an equivalent one that has one equivalent inductor. Let's call it LT, such that the two circuits are equivalent. So here I have Vt and I. Okay. Considering the circuit on the left, I have the inductor and the voltage source in parallel, so they share the same voltage. So now I can write down the voltage across the inductor, Vt, in terms of the current through the inductor through this equation, L di dt, where I is the current through the inductor, which is the same as the current sourced out from our voltage source. So now let's take this equation and do circuit analysis on the circuit on the right to see how we would represent LT in terms of L1 and L2. So far I have an expression for Vt in terms of the equivalent inductance. Now, so let's go to the circuit on the right. So I have my voltage supply, Vt. So now if you wrote a KVL here, we have Vt equal to V1 plus V2. From the previous slide, we have Vt represent terms of the equivalent inductor. So this is what I have here. Now I can write down expression for V1, where V1 is the voltage across L1, as equal to the derivative of the current going through inductor 1 times L1. But since the current going through L1 is the same as the current supplied, because here they are in series, which is also the same as the current going through L2, so I1 is equal to I2 and both are equal to I, and I can get V2, which is the voltage across capacitor 2, as L2 di dt. Now if you look at this right hand side, it can be written as L1 plus L2 times di dt. So in order for this equation to match, I should have LT equal to L1 plus L2. So I could replace these two series inductors with one equivalent inductor whose value is L1 plus L2, and I get the same voltage for the supply. So in general, if I have series inductors, I can reduce them to one equivalent inductor whose inductance is equal to the summation of the individual inductances. Now let's go for a parallel combination. So let's assume that I have a current source here, IT, feeding a parallel network of two inductors. I'd like to replace these two parallel inductors with one equivalent inductor. Let's call it LT. Okay. Note that here all elements are in parallel, so they all must have the same voltage drop V. Okay. For the circuit, we can write down an expression for IT in terms of the equivalent capacitance, because IT here is the same as the current going through that inductor. So IT would equal to 1 over LT integral of V dt, where V here is the voltage across the inductor, which is the same as the voltage across the current source because they are in parallel. Okay, so now I managed to write down the supply current in terms of the equivalent inductance and the voltage across the supply current. Now let's take this result and apply it to the circuit on the right. We do circuit analysis and see how we can get an expression for LT. So here I have IT, and we have this node here. The current N is IT, the current out is I1 and I2. So we can write down this KCL equation. Now I can replace IT with the equations that we derived using the equivalent inductor from the previous slide. So here I have it. And again, remember that they are all in parallel, so they all have the same voltage drop. Okay, now I can use the inductor physics to replace I1. So I1 would be 1 over L1 integral of the voltage across L1, which is the same the voltage across L2, which is the same as the voltage across the current source. Same for I2. I2 would equal to 1 over L2 integral of the voltage across the second inductor. Now, the right hand side of this equation can be written as 1 over L1 plus 1 over L2 times the integral of V dt. So now this is the right hand side, this is the left hand side. For both sides to match, we must have 1 over LT equal to 1 over L1 plus 1 over L2, which is equivalently give you LT equals to L1 L2 divided over L1 plus L2, which is the same combination as if we have parallel resistors. We multiply them together and we divide over the summation. Okay, so in general, if I have more than 2 inductors connected in parallel, I can replace them with one equivalent inductor such that 1 over LT is equal to 1 over L1 plus 1 over L2 plus 1 over Ln. So let's practice that using a simple problem. So here I have 2 nodes, A and B, and I'd like to get the equivalent inductance between the 2 nodes. So we do circuit reduction. So first of all, here I have a series combination. So let's replace that by Ls. So now I have A, I have B, and here I have L1. I replace the series combination between L2 and L3 with one equivalent inductance. Let's call it Ls. Okay, so since L2 and L3 are in series, then Ls would be simply their summation. So we get 40 millihenry. Now we have L1 in parallel to Ls. I can combine them using a parallel equation. So for 2 parallel inductors, the equivalent inductance would be the multiplication divided over the summation. So this gives us 24 millihenry. So in conclusion, we learned in this video about series and parallel connections of inductors, and we learned how to get the equivalent inductance. So for series connection, the equivalent inductance is simply the summation of the individual inductances. For parallel combination, 1 over the equivalent inductance is equal to the summation of the inverse of all inductances. Specifically, if we have 2 inductors in parallel, the equivalent inductor would equal to L1 times L2 over L1 plus L2. Note here that the way we combine the inductance is similar to the way that we combine resistors. If they are in series, we add them together. If they are in parallel, we use this inverse equation. Thank you so much for listening.